Welcome back, everybody. In this video, we're starting to look at section 3.4, which continues our study of polynomial functions. But in this section, the focus is on working with the graphs of polynomial functions. So first, we want to remember how the graph of a polynomial function looks. Graphs of polynomials are always smooth. They don't have any breaks, jumps, or gaps. That would be an example of a graph of a polynomial. It can have some wiggle, that's fine. We know that our quadratic functions, the graphs are nice and smooth. That's a polynomial function. Of course, a linear function is going to be an example of a polynomial function and of course has no discontinuities, jumps or breaks or gaps. So examples of graphs that couldn't be graphs of polynomials would be something with like a corner. That might be something like an absolute value graph would have, or something where there's some sort of a jump discontinuity, or perhaps like 1 over x goes completely undefined right at 0, so the graph is in 2 parts. A polynomial function will always be smooth. It won't have any of this kind of weird behavior. Also, the domain for a polynomial function is always all real numbers, so negative infinity to infinity. Remember that a polynomial function looks like a sub n x to the n plus a sub n minus 1 x n minus 1 and so on. So basically it's a sum of numbers multiplied by variables raised up to powers. And there's no divisions and no kinds of square roots or anything funny happening. So you can substitute any x value you like into your polynomial function, right? So the domain will always be all real numbers. Okay, so that's a little bit of a reminder. So one of the kind of really important features of this section is this set of 4 statements. The 4 statements shown in this box here establish the interrelationships between the zeros of a polynomial, its x-intercepts of its graph, and the factored form for the polynomial. So for this, if p is a polynomial, so throughout this section we'll often be referring to a polynomial p instead of a function f of x, but you can think of it as basically the same thing. So I could have just as well said it if we have f of x here, okay, but they're saying p for polynomial, okay. If p is a polynomial and c is a real number, then the following statements are equivalent. What they mean by saying that they're equivalent is that if one of these statements is true, then they're all true. If statement number 3 is true, then statement number 4 will be true. Conversely, if one of the statements is false, then they're all false. So if statement 2 is false, then statement 4 will be false. They're all true together or all false together. They're equivalent. Okay, so C is a 0 of P. What a 0 of a function is a number that you'd plug into the function to make 0 come out. Okay, so just a quick reminder of how that goes. If you have a function g of x, which is 2x minus 8, what is g of 4? G of 4 is 0, right? So 4 is a 0 of g. Okay, that's the word 0, right? We're not, of course, saying that the number 4 equals the number 0, which is, of course, false. We're talking about a 0 of a function, which is an x value that you'd substitute in, and 0 would come out. So C could be a 0 of p. X equals c is a solution of the equation p of x equals 0. X minus c is a factor of p of x. And c is an x-intercept of the graph of p. Okay, let's go ahead and take a look at all of these in the context of this g that I just made up. Okay, so we can see that 4 is a 0 of g. Okay, let me factor g of x. G of x, if you factor out that common factor of 2, it's 2 times x minus 4. 4 is the 0. X minus 4 is a factor. Okay, if we set g of x equal to 0, that's our 2x minus 8 equals 0. If you solve that for x, you get 4, which is the 0 of the function. And the x minus 4 is a factor for the polynomial. If we were to graph this function, it's a linear function with slope 2 and y-intercept -8. Its x-intercept is going to be at 4, 0. The x-intercept is at 4, and that's consistent with what all the other statements say. So this set of 4 statements and their equivalents is an important part of this section, so you'll want to take note of that. All right, so we're going to use this to help us find some zeros of a polynomial. So here we've got this polynomial 36x squared minus 8x plus 63x minus 14, and we want to find the zeros. So that means we want to know 1, okay, out of the blue box. If we know zeros, we can do that by knowing factors, which is statement 3. So what we'll do is we'll factor f of x, and from there, we'll be able to figure out what the corresponding zeros are. So let's try. So our original function looks like 36x squared minus 8x plus 63x minus 14. So we want to factor that. There are no common factors for all 4 terms, but you'll notice that if we take each group of 2 terms, the first 2 terms and the last 2 terms, that they have a common factor. Here, 36 and 8 have a common factor of 4, and also there's a common factor of x. So if we factor out 4x, we'll be left with 9x minus 2. In the second 2 terms, we have 63x minus 14, and there's a common factor of 7. If we factor out that 7, we'll be left with 9x minus 2. Now you'll notice that the 2 expressions in parentheses are the same as each other. So in other words, our expression that has 2 terms has a common factor of 9x minus 2. So we're going to factor out that 9x minus 2. What's left is 4x plus 7. All right, so we've rewritten f of x in its factored form. And so from there, we can use the result of the blue box. Okay, if we know what the factors are, we can figure out what the zeros are. Okay, so 9x minus 2, we would like to rewrite that so that it looks like x minus c. So let me take 9x minus 2, and we can set that equal to 0. We'll say 9x is equal to 2, x is equal to 2/9. For 4x plus 7, we'll set that equal to 0 also, so that x is -7/4. So the zeros are -7/4 and 2/9. Okay, knowing the factored form, we were able to figure out what the corresponding zeros are. Okay, let's try that again. All right, so this time we're given a function f of x, and again, we would like to figure out what the zeros are. So we're going to try to do this via factoring. So our f of x is 6x cubed plus 22x minus 8x. Sorry, that was 22x squared. So then for this one, we'd first again want to check and see if there's a common factor. And this time there is a common factor of 2x. So let's bring that up. So we have 2x. That will leave us with 3x squared plus 11x minus 4. Okay, so now we want to factor the quadratic inside of the parentheses. And there's a variety of ways of doing that, so pick your favorite method. I do best factoring these things by grouping, so that's what I'm going to do. So to do that, I need to find 2 numbers. I like to call them p and q, so that their product is equal to the product of the 3 and the -4. So 3 times -4, which is -12. And they have to add up to be 11. So p plus q has to be positive 11. So 2 numbers that multiply to -12 but add up to 11 would be 12 and -1. So what we're going to do now is take and rewrite this quadratic polynomial inside of the parentheses, separating that 11x into 12x minus an x. So 3x squared plus 12x minus x minus 4. So that plus 11x we split up into 12x minus x, so that that's equal to 11x, of course. But now you can see that the part inside of parentheses we can factor by grouping, just as we did in this one a few moments ago. All right, so let's try factoring this piece by grouping. So the first two terms have a common factor of 3x. That will leave x plus 4. The second two terms have a common factor of -1. If we factor that out, we'll be left with, again, x plus 4. Okay, 2x, our common factor of x plus 4, and then 3x minus 1. Okay, so the hard part on this is getting that factorization written, but we've done it. So now we just want to identify what the different zeros are. So this f of x will equal 0 if 2x is equal to 0, and that'll happen if x is 0. Or if x plus 4 equals 0, so that x equals -4. Or if 3x minus 1 equals 0, so that x equals 1/3. So our three zeros are going to be -4, 0, and 1/3. I like to write them in order. All right, so there's a couple of examples where we found some zeros by factoring. Okay. All right, so continuing on, still working on graphs, we want to think about how you can tell what the shape of a graph will be near its zero. What I mean by that is this. Taking a look at the graph at where an x-intercept occurs, the graph could, if there's an x-intercept here, the graph could come down and cross through, right? It could cross through the x-axis at its intercept. Or it might just touch the x-axis and come back, okay? Examples of real functions that actually do this would be, of course, our x squared graph. Y equals x squared. It has a 0 at the origin, and of course the graph doesn't cross the x-axis there. But then the graph of our g of x from earlier, 2x minus 8, that crosses the x-axis at 4. So on this function, it crosses the axis at its intercept, but on x squared it does not cross. So does it cross, or does it just kind of bounce off? That's what this part of the lecture is about. Okay, so a little definition first to help us out. P is our polynomial function. If C is a 0 of P, that is P of C equals 0. Okay, let's write that up here. P of C is equal to 0. If P of C is equal to 0 and the corresponding factor, x minus C, right, coming from that box of 4 statements I showed you, the corresponding factor x minus C occurs exactly n times in the factorization of P, then C is a 0 of multiplicity n. So what we're doing is we're defining this idea of a 0 with a certain multiplicity. So let me give you examples of that. So let's say that f of x is equal to x minus 7 squared x plus 3 to the 5th power. Okay, f of 7 is equal to 0, right? And f of -3 is equal to 0. Okay, so these are the two zeros of f. But 7, its corresponding factor is x minus 7, and that occurs twice in the factorization. So this one will have multiplicity 2. For -3, its corresponding factor is x plus 3, and it occurs 5 times in a factorization. So its multiplicity is going to be 5. So the multiplicity for a 0 is just how many times does the corresponding 0 occur in a factorization of that polynomial. It turns out that the behavior of the function at its 0, does it cross or bounce off, depends on whether that multiplicity is an even or odd number. Okay, so to see that, let's take a look at this specific function. Let's let f of x be x minus 5 squared, and that's multiplied by x minus 1 cubed. So let's evaluate f, first of all, at a couple of spots. F of 5, if you plug 5 in here, 5 minus 5 will be 0, 0 squared is 0. We have 0 times something. So f of 5 is 0, and f of 1 also 0. Okay, so those are going to be the two zeros of our f. For the next part, I don't need to know the numerical answer. I just need to know, is the graph or is the function value going to be positive or negative? So let's say we want to find out f of 5.001. So let's pretend we're going to plug that in here. So let's go 5.001. Okay, if you plug in 5.001 for x, minus 5. So just this piece, 5.001 minus 5. Is that positive or negative? It's positive. When you square it, you're going to get a positive number. Okay, so this first factor is going to be positive. Okay, 5.001 minus 1 will be still positive. And then we're raising a positive number to a power, and so we're going to get a positive answer. So this will be positive. 4.999, okay, well, the x minus 1 cubed, 4.999 is pretty far from 1, so we're not going to worry about that. That piece will just give us a positive part. 4.999 minus 5 is negative. Okay, we're taking a negative number and squaring it. Okay, if you take a negative number and square it, you get a positive answer. So this will still be positive. Okay, so you don't have a sign change right at 5. Okay, I just chose like 5 plus 1,000th and 5 minus 1,000th for this, but basically you can see that there's no sign change on either side of 5, and it's because we're raising a positive or negative number to an even power. Okay, when you do the same thing with around 1, we'll see a different result. 1.001. Okay, well, I know whatever I plug in for x, this first whole factor is going to be positive, right? Because we're squaring, right? It's going to be positive. For over here on the right side, we have 1.001 minus 1. Okay, that will be positive. Okay, a positive number raised to the third power is still positive. This will be positive. Okay, but now when you do 0.999 minus 1, that piece is negative. Now you have a positive times a negative, and so it will be negative. And so what's going on here is that the function is 0 right at its x-intercept, okay? If the multiplicity of that 0 is even, you won't have a sign change on either side, like we saw with around 5. If the multiplicity is odd, you'll see that there is a sign change right around that point. Okay, so let's take a look at the graph of this function, and that will kind of confirm what we found out. All right, so here's the graph of our function. You can see that sure enough, there are zeros right at 1 and 5. And then on either side of 5, the function values are positive. And again, that's because we're going to be raising some number, either positive or negative, to an even power, which will give us a positive answer. And then for x values near 5, x minus 1 is nearly 4. So x minus 1 cubed, it will be nearly 64, so positive. But near 1, it depends on which side of 1 we're on. Is it a little bigger than 1 or a little smaller than 1? Will tell us whether or not the graph is above or below that x-axis. So in short, if there is there an even multiplicity, you'll have the graph just bouncing off. If there is odd multiplicity, it'll be crossing through. All right, that takes us to the end of this video. We'll continue working on graphs in the next video.